So I'm going to suppose that you are okay with adding vectors, right? Using components. So I'm not going to go over that because I told you many times. The other thing you have to review, so I don't know if we have time today to get to that, but it's the projectile motion. How to use kinematics equation with projectile motion. So you have to review that. You can look at my older videos or find online tutorials. Projectile motion will help. Okay, the other thing is that you see this is the book here, which is recommended university physics. And it's a very nice book. You don't need to get the last edition. Older edition is fine. But you see it's very nicely explained, and you have all those pictures, illustrations, you see. So that will be chapter 21. So you want to start with chapter 21. What is nice is that they connect a lot with technology. So here they show you how a laser printer is using distribution of charges. And then that's really the first unit. Okay, they see this is called polarization. So this is charged. So it has negative charges here because you comb your hair, for example. So electrons were transferred. Electrons cannot move, they are bound. But you see the papers, little pieces of paper are not charged, but they can get polarized because it's a insulator. So that means all those little molecules, they can be squeezed. The plus goes here, and then the minus goes in the opposite direction. So this is called polarization. It's very important to understand dielectrics. And then you see, this is the best, really, if you want to get deeper, which you should. You see, you have what it's called, I just skip it, but it's a solve problem, right? So the idea is that you're gonna hide the solution. You put a sticker or something, and then you work that on your own. It's a very good preparation if you want to be an engineer. So you know you practice the math skills, because after all, Newton invented calculus to explain the gravitational force, right? So again, I'm saying it again, you have ways that are not very legit to get it, and if you don't know those ways, you can find it very cheap online. There is a website called the Thrift Books, and you will find it, but make sure it starts with chapter 21, because sometimes they divide the books, right? You have 1 to 20 and then 21 to the end. Okay, so you need a book because we have so much time together. And then this is the equation sheet that you should get used to it, to use it when you're doing the homework. So you see here electric field. The electric field is a force per unit charge, so per 1 coulomb. That will be Coulomb's law. Okay, so the force between two charges, it's proportional to the product of the charges, inversely proportional to the distance squared. So it's going to be an inverse square law. And then you have different configurations that we're going to talk about. This is a dipole moment that we will talk about. And you see, you have a little bit of vector analysis, meaning you need to understand what a cross product is or a dot product. This is a dot product. Okay, so it's a very nice equation sheet. It took me a long time to find one like this. Okay, and there is so much time that we have together, so you really have to study. So now we're going to get to distribution of charges. So this is a distribution of charges. So every single one here is going to make its own electric field. And then you have to map the net electric field using what we call the superposition principle. You see, at that point, you want to find the net electric field, so you need to add vectors. So usually it's done with computers. We have like coding, and that's what they do. I don't know what code they use here, but that's what they use, right? They use a computer, and so I can do like a random distribution. So remember, positive charge or positively charged object If it's spherical, you see the electric field is going to be blown away. So positive charge is a source. The electric field always goes outward. Imagine it's like a hair dryer, right? And negative charge, okay, is the opposite. It's a sink. So the electric field goes in. And now, if you have a distribution of charges, so instead of having just a plus or a minus, you see, now the two electric fields will interact with each other. At every single point, they will add up like two vectors, and you have a special configuration. The electric field always goes from plus and up on minus. Okay, so this is minus, electric field goes in. This is plus, the electric field goes out. Now, if you take what we call a test charge, so test charge meaning it's so small, the charge is so small compared to those, it cannot influence the electric field. It cannot change the configuration, cannot change the mapping, but every single point here, I know how is the electric field. So you can imagine this is 1 coulomb of charge, so that means the electric field will be in this direction. Okay, so I can map. It's like you are mapping. So an electric field is a function, and each space, a point in space, you have an electric field. Is that clear? It's a vector field. A vector field were introduced by Michael Faraday. He had this vision, even though he was not good at math because he didn't go to school, but he was very good at experiments, and he had this vision of field lines. So you can have a weird configuration, and then you see there is some kind of coding that will, for every single point, that will find the electric field. Is that clear? So it's a discrete distribution of charges. Okay, so this is the Millikan experiment. So I let you can open your book and see how it's done. I just want to give you the idea because I think you have maybe in the assignment you have something like this. So you have two electrodes. I can show you with an app. You can take a capacitor. Okay, that will give you the idea. So power supply, two electrodes. So I increase the voltage here. So this plate will be charged positively. This one will be charged negatively. And you can visualize the electric field between the plus and the minus. So you can think of this electric field like some kind of stretch spring, the resistance band that you stretch, right? So it wants to bring back the plus to the minus. It's like a spring. So very much like if you take a notebook or a mass on Earth, it's inside the gravitational field. I increase the height. You have an invisible spring here, right? That is stretched out and wants to bring it back to a lower level of energy. So the same thing, the electric field is something that wants to bring the plus to the minus, so the energy goes down. Now you see here, I can disconnect the battery and it's holding the charge. Now you see these lines here are equally spaced. That means it's a uniform electric field. And we're going to see there is an equation for that. There is an equation for that. And we're going to see that. But that's the idea. So you take this configuration here. So you have one electrode which is plus here. And you have an electrode that is minus. Okay, you go from plus to minus. That will be the electric field. It's uniform. It's everywhere the same. That's why it's the same space. Now if you take an electron here, like in that experiment, it wants to go where? Up, up. Always against, because they have a negative mind. So whatever you say, they will say the opposite. So against, right? So that will be the electric force. F equals QE. Q is the charge of an electron. So the charge of an electron is 1.6 times 10 to the negative 19 coulomb, and that will be the notation, charge of an electron. So it wants to go up, but at the same time it has a mass. So the experiment was done with more than one electron. But that's the idea. And that will be gravity mg. Okay, so he did the experiment. I'm summarizing a lot. Okay, you have to open your book to see how it's done. It was very clever. All those physicists at the time, they did such a very smart experiment. And so that way he was able to find the mass of an electron because good morning. The forces will cancel each other out. It was in equilibrium. Maybe not moving, but it reached its terminal speed, so up equals down. Okay, so 1910s, a lot of discoveries at the time. So you have interesting distribution of charges. So this one is plus and plus. Okay, so if I go back here, positive and positive, then take two positive, and it's like collision, right? It's like the electric field push away from each other because positive and positive, they don't like each other. They have a high energy level. That's not good. So they want to push against each other. So now it's like a spring that you compress. So it wants to push away. If you let go, it will accelerate. And you can see that somewhere here, they cancel each other out depending on the charge. Okay, so if I increase the charge, I have to move a little bit further away. Okay, we did a problem like this, right? Now the problem is, okay, I have a video, but I'm going to speed up. So you are mapping the space around. So if you do a Python code, for example, for each single point, you will want to find the net electric field. So the superposition between the electric field because of this one and the electric field because of that one. So it's a net, it's a vector sum. The music, I don't know where they got that music.
Test charge at each point in space is equal to the test charge times the quantity due only to the other charges.
So that will be the test charge, right? Which is 1 coulomb when you are finding the electric field. So you see, for each point, you are doing a vector sum. Now, if the distribution is continuous, then the sum will become an integral.
Electric field. So
So that's what we are doing now. Positive, positive. You see the electric field is like pushing against each other. So sometimes they will give you like an electric field. They don't show you the source. So you have to understand that positive charge will go with the field. Negative charge will go against the field, right? So this vision of a field of forces was from Michael Faraday. He didn't go to school. He didn't go to college. He was not homeschooled, but he was smart, yes. So he's the one who introduced those fields. So if you are into coding, for example, you have Python libraries that very good at visualizing this. Unfortunately, now we have AI, and it's too bad because all those people who learn Python and everything, no software engineer, they're being like replaced by AI, which is not great. So let's see here. Okay, so I just want to do just one example so you can help each other, start to work with each other. I'm not going to go into details because I told you to review adding vectors. So I suppose that everyone knows how to add vectors. So here is the question. Here it's called a bisector. So it's a perpendicular bisector. Okay, so this is the midpoint here between plus and plus, and you want to find the electric field here. Okay, so how do you do it? So you're going to place a 1 coulomb of charge here, okay? Because the electric field is a force per unit charge, and you're going to find the electric field using your vector skills because I told you to review that. So the distance here is y, so that's a given. That distance here is a. Between here and there, it's going to be a, and this is y. So it's a isosceles triangle. Okay, so first you have to draw. So draw, don't stare. Staring doesn't help. Take your notebook or your tablet, and you have to draw first. Why do we want to draw? Because that way we see that maybe some components will cancel out, so we don't have to worry about them. So we are adding vectors, right? So do it, do it, do it, do it. Okay. So first of all, we put a 1 coulomb of charge. So this is 1 coulomb of charge. So from this one, it's going to be pushed away, right? 1 coulomb of charge is always positive. So it's going to be pushed away. Okay. So I'm going to call that E1. And then from that one, it's going to be pushed away, right? Okay. That's easy. And then I told you to review. I told you to review vector analysis. So I'm not going to review that. But you see, you can use the parallelogram method geometrically, and that's going to be the net field. Okay, so you see you are just adding the y component. See, each vector has an x component here, so that's the x component. You go from the tail to the head, you move right side or left side, and then you go up and down. So you have a x component and you have a y component. This one you have a x component and then you have a y component here. Agree? Okay, it's easy. So the x component will cancel out. You agree? Right? They cancel out. They kill each other out. So we only have to worry about the y component that will add up. Okay? The magnitude is the same, right? The magnitude of E1 will be equals to the magnitude of E2. Okay? Because the distance is the same. Agree? So you see that in vector form, E net is just equals to 2 times the y component. Okay, and the y component is the same for both. Okay, so now I'm going to focus on the magnitude. Okay, so this is the magnitude. That's going to be twice the y component. It's easy. I told you to review. Okay. Okay, so do it. Don't wait for me. So the y component. So then we need to find the magnitude, or we can say, first of all, the y component. This is a y component. I'm going to call that angle here alpha. And that's going to be the same as alpha. Okay, and then that distance here is given. It's a, and that distance here is y. Okay, so just apply the equation of the electric field. Is k times the source divided by the distance squared. And the y component, you see, it's a sine. Are you with me? You see, you have a vector. You need to find its y component. So there will be a sine times the magnitude of the vector. The magnitude of the vector is the force per 1 coulomb. So you are using Coulomb's law. Okay, the force is the 1 coulomb times the source, okay, times the distance square, that distance here square. You're doing it? Help each other. If you copy just doesn't help, you have to do it. Okay, that's going to be the magnitude and the sine. Do you agree? Okay, what is the magnitude of E? So E1 equals E2. It's going to be using Coulomb's law, right? So it's going to be K, forgot the K, times what? 1 Coulomb times Q times the distance square, Pythagorean theorem. So it's going to be y squared plus a squared. Agree? It is very basic math. And then the sine equals opposite. This is the opposite side over hypotenuse. Okay, so now plug that into here. Okay, do it. Plug that into here. Okay, you have the magnitude of E1 or E2, and the sine. You plug it in. So you plug that into here, and you plug that into here. Okay, so the net in magnitude, so we're talking about the magnitude, will be equals to 2 times that thing here. This is a 1, okay, because it's 1 coulomb. You place the 1 coulomb here, times K, Q, okay, so you have 2 Q's here, and then over the sine, where is my sine? That will be a Y, And then you have y squared plus a squared. And the square root is just 1/2. So it's going to be k times 2qy. Okay, make sure I don't forget anything. How much is 1/2 and 1? 1/2 plus 1. 3/2. 3/2. Okay, so that will be the electric field at a point P on the bisector. So you get the idea and the methodology to do that. So first you have to draw, you place your 1 coulomb of charge in space, and then you see what are the forces acting on it. Okay, it's going to be pushed here and pushed there, and you add them using vector sum, and then physics stops here. Physics is done. And then everything else here is just math. Okay, you just have to use math. Okay, so then usually what you do, you want to check if this makes sense, and you say, okay, what's going to happen at a distance really big? So we are at a distance like y, the distance here now, I want that to go to infinity. So very, very big, or very big compared to a. Can you find the limit? Find to the limit. Find what's going to happen to this when y here is very big compared to a. So a disappear, you cross, bye. That's how we find limit, right? So when y is very large compared to a, okay, what's going to happen? Do the limit. So it's going to be k 2qy, right, to the limit, and then y squared to the times 3/2. What it's going to be? Are you with me? Y squared times 3/2. Huh? It's going to be y to the 3, right? Okay, so E, it's going to be K. I don't know. I'm going to go here. Okay, so this is math. It's not physics, right? It's not physics because you are taking the limit. Take it to the limit. Always take it to the limit. Y to the 3, and that's going to be E equals 2Q over Y squared. Is it surprising or not? Because if you are very, very, very far away, it's like you have headlights. You're looking at a car and the headlights, you're looking at the headlights, but the car is moving away. The headlights will merge together, right? You cannot take them apart. So if you're moving very, very far away, Q and Q, they merge together and everything happens like you have 2Q. Okay, so from very far away, it seems that you have 2Q. You have 1Q, another Q from far away. So that makes sense. So that's how you check. Are you okay? Yes? Okay, it's not that hard. Yes. The K, it went on vacation. Thank you. Went to Italy. Italy is the best place in the world. If you want to visit a nice place, go to Italy. So yes, so thank you. Okay, it's not supposed to go anywhere. It's supposed to stay here. Okay? So we have this expression here, 2qy, and if so if you are in engineering, you want to understand what's going on, right? So you want to visualize that function. So I don't know, maybe you have another simulation. I only use this one because it was already hard to get how to use it. So f of x, so I'm gonna plug in this equation here. So you have a k, so I don't care about the k right here because I just want to find the the behavior. So I don't care about the Q. I'm just gonna put here, and you should do it as I'm doing it. I want to have the behavior of this here. So you have we can skip the, we can skip, we're gonna keep this, right? And not the Q, just to see what it looks like. So you have a Q, we don't care, 2 times X, okay? There is a X at the numerator, and at the denominator you have a X square or Y square, doesn't matter, plus, and I'm going to give myself a number. I'm going to say it's going to be 2. I'm going to say A equals 2, because you have to come up with something. You cannot put an A here. So 2 squared is 4. So, and here I'm going to put graph. Okay, and here you have a what? You have a 1.5, agree? Let's not forget the 1.5. Okay, for X between 0 and 10. Okay, that looks good. And this is the function here. So it means, what it means? It means as you move along the bisector, okay, you're gonna reach here a maximum when y equals 2, and then it's gonna decrease. So it's very important to know how to do that, because then you have a better understanding. So what does it mean? It means as you move along that line, the electric field is going to increase. It's going to reach a maximum when this distance equals to that distance, right? And then it's going to decrease. You want that to decrease because at infinity, okay, there is no more electric field. So it gives you a gut feeling of what's going on. Okay, so it's a very nice way to understand. Okay, are we good? Okay, so very, very important for chemistry and biology as well, dipoles. So a dipole happens when you have a plus and a minus, but the charge, the magnitude of the charge is the same. So you have a Q and you have a minus Q. So the electric field will go from the plus to the minus. Okay, so water molecule is polarized, a molecule of soap is polarized. So sometimes you have permanent dipole, so they stay a dipole forever, like water molecule. Also, sometimes they can get polarized. They can be polarized. If they are placed inside an electric field, they will be polarized. So those little seeds here get polarized. Okay, so that will be very important for the configurations. That's called a dipole. So we're going to define a new physical quantity, which is called a dipole moment vector. The notation is P. So this vector goes always from minus to plus. And the equation of the dipole moment is Q times the distance. Because in chemistry, when you have or biology, like very small scale biology, you don't want to deal with this distance here. This distance is going to be super small. So instead, we package the distance inside P with Q. So we just, to understand how the molecules will behave, we just multiply Q by D, and D is the distance between the minus and the plus. And the vector goes from minus to plus. Is that clear? Okay, so water molecule is polarized, and you have a minus, which is the oxygen. Hydrogen is plus. So oxygen takes the 2 electron, and the hydrogen gives away the 2 electron. So for a dipole, you have minus and plus. So before we had plus and plus. So far away, you have 2Q, right? The plus and plus, 1 and 1 is 2. But here you have a minus 1 and a 1. So very far away, very quickly, it's going to decrease faster. So from very far away, instead of having as you move away from the dipole, the behavior is not 1 over r squared, it's going to be 1 over r cubed. Because plus and minus, as you move away, they merge together and they cancel each other. So it doesn't have a behavior in 1 over r squared, like the one we've seen before, which is 2q over r squared. Now it's 1 over r cubed. Is that clear? Okay, so I'm going to just throw at you the equation, because usually with those molecules, we are not very close to the molecules, right? The distance between the two poles, so the oxygen and the hydrogen, is very small. So you are always far away. And when you say you are far away, it's always relative to what? You're always far away from that distance here because the molecules are so small. So when we do the math, and we take the limit, if you are on that bisector here, you can show, doing the math, that's going to be the electric field. And you see there is a distance cubed at the denominator. So it means if you move on that bisector far away, that will be the equation for that. Okay, and this is Q times D is your dipole moment. It's your dipole. Is that clear? It's just an equation. That's how it works. As you move away on the bisector, you're always far from that distance. I mean, it's always larger than that distance. We can show taking the limit, doing the math, that's going to be what you're going to get. And we're going to do the math for one, not for both, but for one. Okay? Now, if you move along the axis, so that is called the axis, that's what you get. Okay, so it will be you have a 2 here and you don't have a 2 there, over the distance cube. There is nothing to understand, there is just to say okay. Are you saying okay? Okay? If you take the limit, you do the math, and then you take the limit, that's what you will get. And that's what they use in chemistry or biology at a small scale, molecular biology. Okay, that's what it's called, because the distance between the poles inside the molecule is so small. Are you with me? Okay, so let's do an example just for you to see how it's done. Okay, so we're going to go on the bisector. Okay, so you take a point on the bisector, that will be the distance y, like we did before, and that will be the distance a. So the distance between q and minus q is 2a. That will be your d in the dipole moment. Okay, so can you try algebraically to find the electric field here at that point? Adding vectors, meaning you're going to look at the components and you're going to see which components cancel each other. Okay, so now we're going to deal with cosine and not sine. Okay, so you see when you add the components, you use the parallelogram method. So imagine you have a 1q, one charge, 1 coulomb. 1 coulomb of charge is going to be attracted here. 1 coulomb of charge is going to be pushed away. And then you do your parallelogram method, that will be the net electric field, which is the force on 1 coulomb of charge. So you need to find the magnitude of this. You see that now it's the x components that will add up. The y component kill each other out. Okay, go. Go for it. So at that point, once you have this drawing, the physics is done. Okay, it's no more physics, right? It's just math. And math you need, if you go to engineering, you need the math. Okay, so each has an x component. Okay, this one has an x component. This one has a y component, and this one has a y component. They kill each other out. Okay, so y and in magnitude. Okay, so that means the y component equals 0. So we want to find E is the vector sum of E1 plus E2. You use the parallelogram method, and you see that the y component, there is none because it kills each other out. So the 2x component will add up to E. Okay, so E, the net electric field, is just 2 times the x component of 1, for example. It doesn't matter that they both have the same component. So is that clear? And the x component, do it. Okay. X component, the x component, easy, it's a cosine. You see, it's a cosine. That angle here is the same as this one, right? So it will be the magnitude of E cosine alpha. That's why I told you review how to add vectors. You need to add the components. See that angle here, the same as that one. Do you agree? Right? Nothing to stare. Do it. The more you do, easy it will get. Okay. So E, it's gonna be Coulomb's law. So it's okay. You can imagine you have a 1 Coulomb of charge. It's gonna be a Q. And then here again we have the distance square, which is a square plus y square. And the cosine is adjacent, which is a over hypotenuse. That will be for one x component. So the x component of one of them. And you add the x component. So the net field, so the net one, okay, in magnitude will be twice that. So it's going to be 2 times a, and then you have a k, and you have a q, and that's going to be a square plus y square, and then it's going to be 3/2. Is that right? Are you with me? Yes? It's a physics one, just adding vectors. You really have to, you cannot survive if you don't know vectors. Chapter 1 of your book, yes.
Still, for the electric field is still the bottom one is r squared, right? Or is it r cubed?
Okay, we're going to see that. Because you see, in that case, there is no y at the numerator. Okay, it's a good question. When we're going to take the limit and see what's going to happen. Previously, on this show, you have a plus and a plus, and you had a y at the numerator. Here, there is no y at the numerator. Now, the dipole moment equals 2a times q, right? Because by definition, the vector moment is the distance between the charges times q. So I'm going to hide that as the net field equals, you have a k, and there is a p, and there is a square plus y square, 3/2. Okay, now take the limit. To the limit, take it to the limit, okay? So that means take it to the limit, meaning that y, now we go very far away. You don't have to go very far away because that distance is very small. With a molecule, so this distance is very small. So take the limit. What's going to happen? Okay, pure. So this one get vanish. Bye-bye. And this one you get times 3/2. So what you're going to get at the denominator? Yeah, y to the third. Okay, so with a dipole will decrease the electric field, the magnitude will decrease very quickly because as you move away, they merge together. So minus and plus destroy each other. You can do the same kind of a computation. So this is for the perpendicular bisector, but you can do the same thing along the axis. Okay? Now if you do it with Wolfram alpha, so it's going to be the same thing as before, but we don't have an x. There is no x here. Is there okay? So now it keeps decreasing, and the behavior when it's really big will be 1 over x to a third. So it doesn't go up and go down, it keeps decreasing. Okay, so this is again a dipole is a vector. It goes from minus to plus. This is the distance between the minus and plus. So that will be it's a vector. The dipole dipole moment is a vector, and very far away, that's what you get. Okay. You can write the electric field this way because you see the electric field points from plus to minus to the right, but the dipole points in the opposite direction. So that's why you have a minus. And K, the electric constant, you can write it as 1 over 4 pi epsilon 0. Any questions? Okay, so if you want to know, so now we can do the same computation along the axis. So like you take a point here along the axis and you can find the electric field, and at the end, if you take the distance at a very far away distance, that's what you get. You can look at the computation, but the same idea, you are adding vectors and then you take the limit. Are you with me? It's not that hard. So if I ask you conceptual question, you have a dipole, so the electric field from a dipole. By the way, the unit for a dipole is Coulomb meters. Okay, because charge is in Coulomb and the distance is in meters. So you have an electric field which is 800 Newton per Coulomb. So it will experience a force of 800 Newton if you place a 1 Coulomb of charge. So far away, you double the distance, and we suppose it's far away because the dipole is very small, so very far away. What's going to be the electric field? See? So it goes as 1 of the distance to a third. So 2 times 2 times 2 is 8. So 8 divided by 8 is 100. So the answer is C. Okay, so typical conceptual question. A dipole decrease as the distance cube. Okay, so now we look at this configuration here. So this is a capacitor, kind of a capacitor. Okay, like this. So two conductors, one is charged positively, one is charged negatively. And what you see here is that the electric field is uniform. And an electric field is a conservative field, meaning if you take, so think of gravity, so gravitational field here next to the Earth, remember it's 9.8, so it's uniform, right? If you don't go very far, it's uniform. If you take a mass from point A to point B, you have to do work. I'm doing work to increase the potential energy. But that work doesn't depend on the path. Doesn't matter if I go this or if I go boom, 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 I go to the library and I go back to here, the work done will be the same. So we say gravitational field is conservative. So it's storing energy, like in that little spring, energy is stored, and then I can get it back. Okay, so we say gravitational field is conservative because it doesn't depend on the path. if I go from here, boom, 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 I come back to there, the work done is 0. There was no work done because I go back to the same place. Okay, so I'm doing work against gravity. Okay, and gravity is doing negative work, and now it's the opposite, right? So anyway, if you have a charge in an electric field, it will be experiencing a force F equals QE. Likewise, a mass experiences a force F equals mg. The field is G, the field is E. G, you can think of that as the force per unit mass. E is the force per unit charge. The electric field is uniform. Okay, so you can visualize the electric field between the two plates with those little seeds and castor oil. I think I already showed you that. And if you do that, you see that it's uniform. Outside, you see it's randomly placed. You see there is no pattern outside. So outside, we will show that later, but the outside there is no electric field. Electric field is only between those two plates. This is called a capacitor. Is that clear? And again, if you look at the simulation here, it goes from each plus goes to minus because it's like it's trying to bring them together. That's what happens. If you put too much charge, you have a discharge, and there is a breakdown the electric field because it wins, bring the charges together. Okay. And this is what we can use in demo, for example. So one plate, and the second plate is connected to ground. Okay, there is a connection to ground. So you can charge this one, for example, just using static. Okay, you rub, for example, silk and glass, why not? So that one will be charged negatively. And then because it's connected to ground, all of a sudden that will be plus. So you have minus and plus, you can disconnect and you can hold the charge. That's one way to do it. Second way to do it, you can apply power supply. A battery, it's no, 5,000 volt will be better with power supply. Okay, so I'm going to just give you the equation for the electric field. And then we have to wait for Gauss law, which is next unit, to prove why is that so. So the electric field between those two plates, okay, is uniform, and it's going to be equals to the charge. Okay, so you have the same charge here and the same charge there. This one is positive, this one is negative. The same charge, okay, the same charge divided by the area of the plates. So it could be a pi r squared in that case, or if it's a rectangle, it could be width times length. Okay, so the area epsilon 0. Okay, epsilon 0 is a constant. Agree? This is an equation. It goes from plus to minus. And then that's when calculus starts to kick in a little bit here because we're going to define a charge density sigma. Okay? So surface charge density, which is the charge per unit area. Why? Because those charges, there are so many of them that we cannot say, we can only define the density. So I was trying to find a way to visualize that. That's AI. It's not perfect, but it gets better. So imagine these are all charges on the capacitors. That's what AI came up with, okay? All right, that's the best. I tried many times. That's the best I could get. So let's say these are all positive charges on one plate of the capacitor. So this, if you compute all those charges, right? So if Q is the sum of all those little charges, right? So that will be the plus Q. So everything is plus Q. Now, if you take a small area here, right? Let's say it's 1 meter per 1 meter, just to simplify. That will be the density here. That will be your charge density. That will be how much charge you have on that 1 unit area. So that's going to be Q divided by the area. Okay. So the area here This is the area A. So you divide the charge by the area, you get the density. And what is the density? It's just the charge per unit area. So 1 meter per 1 meter, that will be the density. That's the meaning of that, okay? Coulomb per meter square. Okay? So that's the meaning of a density. I'm sure you know that from chemistry. Okay, so try to do this one. I think there is a TMI somewhere. Sometimes they like to trick students with TMI. I forgot. So anyway, you can do it. Help each other. Okay, it will help if you help each other. You don't have to discuss your breakfast, but you can talk about physics. That's fine. Okay, so what are these equations that we have? We know that the electric field is sigma over epsilon zero. What else do we have? We know that sigma is the surface charge density, so it's Q over A. Okay, what else do we have? We know that the charge is quantized. So any charge is because you have that many electrons missing or gain. So any charge is quantized. So it's going to be the number of missing electron or the number of gain electron times E. Okay, and you know the charge of an electron. And what else do we know? Epsilon 0 is 8.85 times 10 to negative 12 and units here. Okay, so you can use, first of all, you can find the charge density, the density. Do we have the density? Do we have the density? No, we have electric field. Ah, we have the electric field. Okay, so we can use this equation. That will be my equation 1. Thank you. Equation 1. Equation 1, the density equals E times epsilon 0, right? Okay, you cross multiply. Right? You do it? I'm just using this equation, right? I'm just plugging in. So 18,000 divided by 8.85 times 10 to the negative 12. That's going to give me
1.59 times 10 to the negative 7.
right. Negative 7? Okay. What's your name? What's your name?
Adia.
Adia? Yes. You all agree it's negative 7? Okay. Coulomb per meter square. Okay? Okay, so once I have that, I'm going to use this equation here. So I can find the charge. Because the ultimate question is to find the charge. See, they give you TMI. You see? They try to trick you because if you make a drawing, you have a plate and you have another plate here. And this is 22 centimeters. This is 22 centimeters. And the distance between them is 1.5. So the distance doesn't matter exactly. They try to trick you. If you take the MCAT, that's what they do. Oh, of course, it's much easier than that. So, but you have a TMI. So the area of a square is 0.22 square, width times length. So the charge equals sigma times the area. Okay, so it's 1.5 times 10 to negative 7 divided multiplied by 0.22. Is that square? Square, right? I don't know because I did a mistake. I used 1.5, which I should not. So what do you get?
7.69 times 10 to the negative.
Negative? Negative what?
Negative 9.
9. Okay, do you agree? 10 to negative 9, everyone? So it's nano, right? So 7.7 nanocoulomb. Agree? Okay. 3, I'm going to use this one. Right? So you're right. So this is an integer. Okay, it's going to be Q divided by the elementary charge. So it's going to be 7.69 times 10 to the negative 9 divided by 1.6 times 10 to the negative 19. So it's going to be a 10 to the 10. Huh?
I think it's 4.8 times 10 to the 10.
4.8 times 10 to the 10. Thank you. Electrons. Agree? Any question? Okay. So this one, it might come from the book. I don't know where it comes from. Okay, so that's see, this is projectile motion. So just to remember projectile motion from last semester. Okay, let's see. I'm shooting horizontally. So you're gonna have two axes, right? You have the x-axis and y-axis. And then we can divide the motion into two components. Along the x-axis, it's moving at a constant speed because along the x-axis, there is no force. Along the y-axis, it's going to speed up because you have the force due to gravity. So along the y-axis, there is an acceleration. Along the x-axis, there is no acceleration. So you have two motion happening at the same time. Along the x-axis, you have a uniform motion. So every second, the same distance is covered. But along the y-axis, there is a force down. There is an acceleration, and it's accelerating. So every second, it's going to move faster. The distance is going to increase. So you have two sets of equations, one for the x-axis, one for the y-axis. Along the x-axis, the speed stays the same. Along the y-axis, the speed increases at a rate of g, the acceleration due to gravity. Okay, so that's just a flashback from last semester. That's how it works. Fire! You see, the x component doesn't stays the same, the y component increases. Okay, so to use math, to analyze those motion, then we have two sets of equations, one for the x component, one for the y component. If along the x component there is no acceleration, I just have two equations here. Okay, so that will be the distance. It's a uniform motion. And then along the y-axis, I'm going to have something like this with an acceleration. What's the point of that? The point of that is the following. Okay, and it's easy if you remember projectile motion. If you have an electron going through that region here where you have an electric field, it wants to go which way? Where is the force? Opposite of the electric field, so it's going to be down, right? It's going to be down. So it wants to go down, but at the same time is also moving forward. So when you combine those, you get a nice parabola with two sets of equations. Okay, so the electron, let's say the electron here, that will be your force. Okay, so F, you see the force equals the charge of an electron, or Q, depends what charge you have, times the electric field. So there is a force down, which means that you have an acceleration. The acceleration is the force divided by the mass, so it's going to be E. So that will be the force here divided by the mass. But that acceleration is along the x-axis or y-axis? Y. Okay, so the component of the acceleration along the x is going to be 0, and along the y, it's going to be the force, so the charge times the electric field divided by the mass. Along the z-axis, there is no acceleration. Okay? So along the x-axis, nothing exciting happening. The velocity stays the same, and the displacement is just the initial velocity, I, times the time. Nothing exciting. And along the y-axis, you see the displacement equals initial velocity, no, there is no initial velocity, minus the acceleration, which is this, t squared, and I'm missing something. Do you remember from physics 1? 1/2. 1/2 at squared. Okay, remember projectile motion, you can go back today. The velocity along the y equals the initial minus at. Agree? So it's very much like projectile motion. You have to divide. Galileo came up with that any motion can be divided into components, and the components are ignoring each other. They are independent from each other. Okay. So that will be a typical motion in a cathode ray tube. So here, for example, so that's what they use in the old computers. And that's why the computers were so bulky, because instead of having diodes and transistors, PN junctions, they use those bulky things. So that way you can control the current, right? So go 1, don't go 0, but it's very bulky. So anyway, if you shoot an electron, so you see you make a, so first of all, between the minus and the plus, the electron will accelerate, and you trick the electron because you make a hole, so it's overshooting, right? It's gonna pass. And then here you apply an electric field, so the electron will curve up. It will make a parabola. So this is like projectile motion upside down. Agree? So you're gonna have two sets of equations. One for the x-axis, it's uniform, and one for the y-axis, which will be accelerating. You're gonna have an acceleration. Agree? The old TV had those cathode tube. Back. back in time. Donc now it's not going to open, of course. No, I don't know what's going on. Ah, takes a lot of time. And it's not the right one. It's not the right one. You don't see it, right? It's okay. We give our brain a little rest. It's fine. Come on, come on. Okay. Cathode ray tube. Okay, so you have two electrodes. I'm gonna apply a voltage, and I'm gonna shoot an electron. So which way do you think it's gonna go? Up. Right. So here it's accelerating, moving at a constant speed, and now it's gonna be deflected up. And the typical question, so here usually you have a screen, will be find that distance here, delta y. Okay, so delta y will be the y displacement. You will have delta x. So the acceleration is only along the y component. Now I can change the voltage, and now the electron is going to go down like a projectile motion. Okay, I have to go faster. I have to go faster. Okay, just there is always a tricky question for the test, right? So let's say you have a minus, minus, and you have an electron here moving. So what's going to happen? Is it accelerating, slowing down, or moving at a constant speed? Accelerating, right? So the electron, very good. The electron, what's your name? Huh? Yeah. What? Lamy. Yes, exactly. It's going to accelerate, and the acceleration will be in magnitude. Okay, it's going to be the Q, the E divided by the mass. So it's going to accelerate. So it means it's going to move faster and faster and faster. If there is a hole, it's going to go through it or it's going to crash. So this is very much like something falling. It's going to speed up. And then there is always a trick here. Let's say now this is positive and this is negative. What's going to happen now? So it has velocity to begin with. So it has some momentum. Slowing down. So it's going to slow down and then it's going to turn back. Okay, so this is very much like physics 1. You take a mass, okay, you throw it up, it's going to slow down, stop, and then come back. Slow down, stop, and come back. So with those problems here, you have to be very careful that I don't try to trick you. Okay. Yes.
I have a question. If you launch the electron at the like negative plate, will it ever like touch the plate?
It depends. It depends on the this one or that one.
Yeah.
This one. It depends on the inertia. Not inertia. Momentum. It depends on the speed. So if I throw something in the air, but I throw it, hard enough, it can touch the ceiling. So it depends on the velocity, initial velocity. Yes.
So if I've understood this, you can basically, since we're working with an electron, you can basically think of the positive side of the plate as always being the ground that the electron wants to move towards now.
Yes,
And
exactly.
like in gravity, it's always going to drop towards.
Exactly. Yeah, so it will be the same thing as physics 1.
Oh.
Except you're right, the plus will be your ground. Yeah, you can think of that like this. I didn't think of that. So you take your head, you do this, and that will be the ground, go up and down. Okay, that's a good suggestion. You can do that, right? So plus is the ground for the electron, and it wants to go to the ground. If it's plus, it will be the opposite. Okay, that's a good way to remember. Okay, so that's from your book 21.7. You can do that. So that will be the acceleration is the force divided by the mass. So that will be plus, that will be minus, and the electron wants to go to the plus. So it's like a projectile motion upside down. Okay, so this one is a little bit challenging. So before we go to that, I just want to review. At what time does it open? The 11, right? Maybe here. Can you see this one or that one? So the coordinate system is based on the right hand. Sorry for the lefty. So it goes x. So you have to do this. That's going to be very useful for what coming up because of the cross product. You need to know how to do this. So this is x. If this is x, that will be y, and that will be z. Okay. So it's a right coordinate system. Now you don't have to do x, y, z. So z is always followed by x. So you can do z, okay, x, y. So you can take z, x, y. Or you can do y, z, x. Okay, you can see that here. If you let me click on it. Okay, so if this is x, y, z, z, x, y, y, z, x. So it has to be in this order. Why is it important? Because your page or your paper is only 2D. So you can fit only 2 axes. And then the third axis has to go into your screen or into your paper or towards you. So the third axis, when it goes into the screen or into the paper, you're going to show it as a cross. Okay? Go in, it's a cross. Towards you, it's a dot. Okay? So for example, if you want to work with the z and x axis, you want to make sure that z is this way, x is that way, y is towards you. So it's going to be a dot. Okay? Or you can work with the y and z, x is towards you. If you x, y, z, it's going to be towards you. If it's into the screen, could be, could be. If I do that, it's towards you this way. Then you have a x. Okay, so that's going to be the right hand rule. You see, z, x, y. Okay, so how are we going to apply that to this problem? Because in this problem, they talk about E field along the z-axis. So I need a z-axis on the paper. I need a z-axis on the paper. And then they talk about velocity. No, what do they say? E field with the initial no, the velocity is along the z-axis, so I need the z-axis on the paper for the velocity, and the electric field is along the y, so I need a y and a z on the paper, right? Because otherwise it's too much headache, right? So you take your right hand, y, okay, what comes after y? Z. Okay, so X is towards you. Yes? Okay, so I'm going to make a X with a dot. Once you have done that, it gets easier. Because if you don't do that and you keep your X, Y, Z, oh my God, it's too much headache. Okay, you want to make sure that the plane you are working on is on the paper. Okay? So at least, I don't know if we'll have time to do everything, but once you understand that, it's not that hard. You see, I did it here for you. So it's moving here. So draw the electric field. Draw the electric field. And then is it a negative charge? So it's a negative charge. And then find out which way it's going to move. So draw. So always draw first, right? So you draw the electric field and then you find out which way it's going to move. Okay, and the acceleration is the force divided by the mass. Okay, don't stare, no use, don't stare. Do it.
Since the charge is negative, it would move in the opposite direction as the field, right?
Exactly. So the electric field is along, where is the electric field?
It's along the y.
The positive Y or negative Y? Oh, the positive. Okay, so you're right. So the electric field is this way. Because it's a negative have a negative mind. He wants to go down. Exactly. So he wants to go down. So the force here equals QE. Exactly. So there is only acceleration along the force, right? F equals ma. So force is proportional to the acceleration. So they have the same direction. So the acceleration is going to be down. So I want to go in a straight line at a constant speed. No, you can't. You have to fall. Okay. So along the y, it's going to accelerate down. Along the x, it's going to move at a constant speed. Okay, review projectile motion. Two things happening at the same time. It's accelerating only along the y-axis, and it's moving at a constant speed along the z-axis. So along the and the x, I forgot the x is towards you. So the x component equals 0. The y component of the acceleration is the force, but it's negative, right? And the z equals 0. So it's going to be minus 3. Electric field is 500. And the mass. What do you get?
Wait. Oh, ah.
Get that? Okay, so you have to review vectors, projectile motion, and then dot product and cross product, and the right hand rule. Yeah. Meter per second. A meter per second per second. Okay, what do they say? So if they want to find the time and they give you delta y. So delta y is given. Find the time. So along the y, there is an acceleration. So look back at your kinematic equation. Kinematic equations say that the y displacement equals initial velocity times time plus 1/2 acceleration t squared, right? From kinematics, the displacement, how far you're going to go, depends on the initial velocity and the acceleration at the time elapsed.
It's zero.
Zero, right? No initial velocity along the y. It's 0 plus 1/2 the acceleration, the time square. And I did a mistake. It should be minus. There is a minus here because the displacement, see, that will be your displacement. That's delta y here. The displacement is negative. This is delta y. I'm going to save that. And that will be delta x for next time. Save as. That's a x displacement. Okay, and you find. Okay, so with your calculator, you're going to 10 to the 8. If you have any question, here after 10 to the 8 divided by, open the parentheses. So you do 2 times 10 to the 8. Okay, you don't have to do that. Divide by 7.5, 10 to the 6, and you take the square root, right? Yeah, you should not have any more. Let's see. 10 to the 8, the square, okay? Don't forget to square. So 10 to the 8, okay? You multiply by 2.
So it's just 16.
Okay, and you divide by, open the parenthesis, 7.5 times 10 to the 6. Okay, and then you take the square root. Square root, call back the answer here. So second minus. Yeah, 5.15 seconds. You see, make sure you have parentheses. If you don't put parentheses, it's pandas, so it's going to divide by 7.5 and multiply by 10 to the 6. Okay, so we'll finish next time, but I'm running out of battery. Delta, is there a delta X, by the way? Is it moving? No. And the delta Z is just V0 times time. Okay, the delta Z is just the speed times the time because there is no acceleration. So this is just projectile motion.